Hello everyone. Welcome to the Learn Circuit tutorial. This is the second video on node analysis. Let us start with a review. The first video discussed the main concepts of node analysis and the major steps of using it. Then, we talked about the passive sign convention, and finally, we discussed how to label current directions. In this video, we will practice node analysis using the following two examples. Let us start with example 2. We need to determine the node voltages and branch currents. This example is very similar to example 1, with one more resistor added to the top. There are 3 steps to use node analysis as follows. Before we start to apply these steps, there are 4 questions you can ask yourself. How many nodes are there? Which node should be selected as the reference node? Which node voltages are known? Which node voltages are unknown? Pause the video and think about those questions. In this example, there are 4 nodes. The step 1 is to select a reference node and label non-reference node voltages. We select the bottom node as the reference node, and its voltage becomes 0 volt. Then, the voltage at node 2 is 6 volt because Vs1 connect node 2 and the reference node. Similarly, the voltage at node 3 is 3 volt because of Vs2. If the reason here is not clear to you, I recommend you to watch the first video on node analysis. The only unknown voltage is V1. Then we just label it. We do not need to label V2 and V3 because we know their node voltages. Now step 1 is done. The next step is to label current directions and write KCL. I also want to remind you the KCL equations. You may copy this down to a paper because we will refer to these equations later. As discussed earlier, the current direction does not matter. Let's go ahead and label them all to flow away from node 1. Then, we will have the KCL equation as I1 plus I2 plus I3 equals 0. Express it with V1. The equation becomes V1 minus 6 over 6 plus V1 over 3 plus V1 minus 3 over 6 equals 0. As discussed in the first video, the advantage here is that it is always V1 minus another node voltage in each term. In addition, all terms are added together and equal 0. If you write an equation like this, could you possibly make a mistake? No way, right? In step 3, we can solve the equation. The solution is V1 equals 2.25 volt. Now we have solved the unknown node voltage V1. Let's go ahead and find all the branch currents. Let's first label the remaining branch currents, including the current I4 that going through R4, the current IV1 that going through the first voltage source, and the current IV2 going through the second voltage source. Using Ohm's law, we can determine I1, I2, I3, and I4. I1, I2, and I3 are exactly the same as example 1. The difference from example 1 is the current going through the 2 voltage sources. Let's find them. To find the current going through the first voltage source, IV1, let's write KCL for node 2. Noted that we used equation B to write the KCL. We need to one-step algebra, and we find IV1 equals I4 minus I1. Note I1 is negative. Then, plug in numbers we can calculate IV1 is 1.375. Now, let's write KCL for node 3. We can consider this as using equation B or equation D. Again, we do one-step algebra, and we find IV2 equals negative I3 minus I4. Then, plug in numbers we can calculate IV2 is minus 0.625 amp. We define the current of IV2, leaving the positive terminal of Vs2. We find IV2 is negative. This means the current actually enters the positive terminal of Vs2, which may be counterintuitive to some people. While An analogy you can consider here is charging a battery. Finally, we can summarize the branch currents as follows. A final comment is that, using node analysis, no matter what the question asks you to determine, our goal is to find node voltages. Once we find node voltages, everything about this circuit will be known. You can also check out the website learncircuits.net. The current directions for this example were labeled differently. Now, let's move on to example 3. We need to determine VR3. The polarity is already labeled in the circuit. There are 3 steps to use node analysis as follows. Let's start with our usual questions. How many nodes are there? Which node should be selected as the reference node? Which node voltages are known? Which node voltages are unknown? Pause the video and think about those questions. We will try 2 different methods to label the current directions. In the first method, we label the current direction based on our best guess. In the second method, we label all currents flowing away from the non-reference nodes. I hope that at this point, you are comfortable with speeding up the circuit solving progress. Let's select the bottom node as the reference node, as usual, and label the current directions as shown in the circuit as the first method. Note that I3 is labeled from left to right to follow passive sign convention, entering the positive terminal of R3. At which nodes do we know the voltages? Because of the 2 voltage sources, we know V3 is 6 volts and V4 is negative 3 volts. V4 is negative 3 volts because of the polarity of Vs2. The positive terminal is connected to the ground, and the negative terminal is connected to node 4. The voltage from 0 volts drops 3 volts to node 4, so V4 is negative 3 volts. We need to pay attention to voltage source polarities. The unknown voltage is V1 and V2. Y are labeled in the circuit. We are ready to write KCLs for the 2 nodes, and we will use equation B. We directly write KCL based on V1 and V2. The equation is 6 minus V1 over 6, that is I1. This term has a positive sign because I1 enters node 1. Then, minus V1 over 3, that is I2. This term has a minus sign because I2 leaves node 1. Then, minus V1 minus V2 over 6, that is I3. This term has a minus sign because I3 leaves node 1. Then the equation equals 0. Similarly, the KCL for node 2 is V1 minus V2 over 6, that is I3. This term has a positive sign because I3 enters node 2. Then minus V2 over 4, that is I4. This term has a minus sign because I4 leaves node 2. Then minus V2 minus 3 over 2, that is I5. This term has a minus sign because I5 leaves node 2. This term has double minus 3. It will end up V2 plus 3. Finally, the equation equals 0. In step 3, we can solve the 2 linear equations with 2 unknowns. Do some algebra. The 2 KCL become as follows. We can solve them using Gaussian elimination method. Equation 1 times 2 plus equation 2 will eliminate V1. Then we can solve V2 equals minus 1.43 volts. Then substitute V2 in the first equation. We will find V1 equals 1.14 volts. Now we have solved the unknown node voltages V1 and V2. We can then find VR3 is V1 minus V2 equals 2.57 volts. Now, let's move on to the method 2. We labeled all currents flowing away from the node 1 and node 2. For node 1, we have I1A plus I2 plus I3 equals 0. Express this equation with V1 and V2. The KCL for node 1 is V1 minus 6 over 6 plus V1 over 3 plus V1 minus V2 over 6. Then the equation equals 0. As can be seen, V1 is leading all the terms, and all terms are added together and equal 0. So, you don't need to worry about which node voltage is leading the term. In addition, you don't need to worry about the sign of the term. For example, Entering the node is positive or negative. For node 2, we have I3b plus I4 plus I5 equals 0. The KCL for node 2 is V2 minus V1 over 6 plus V2 over 4 plus V2 minus 3 over 2 equals 0. As can be seen, V2 is leading all the terms, and all terms are added together and equal 0. A further comment. For the branch with R3, we define two currents, I3A and I3B, which are against each other. This is totally fine. I3A is labeled for node 1 KCL. I3B is labeled for node 2 KCL. They are essentially the same. Their directions are opposite. Their magnitudes are also negative to each other. Apparently, I3A equals V1 minus V2 over 6, and I3B equals V2 minus V1 over 6. Let us compare with method 1. Apparently, if we do some algebra, the two KCL equations in method 1 are the same to the method 2. As discussed earlier, method 2 has certain advantages. However, you just need to pick the method that you like better. That's it for this video. I hope you find it helpful. If you have any questions, please leave a comment below. Thank you for watching. Visit learncircuits.net for more information. See you next time.